Every great solution begins with identifying a real problem. That quote really hit home for me during my internship at the Environment Protection and Climate Change Department, or EPNCCD, in Punjab. I went in totally expecting to focus on the usual suspects of air pollution. Exhaust pipes, factory smokestacks, all that. But through my fieldwork, I quickly realized that one of the absolute biggest contributors to our environmental crisis is just hiding in plain sight, completely overlooked. We're literally talking about the ground we're building our future on.
Okay, let's dive into this explainer. Welcome to Engineering a Cleaner Future. Today, I want to take you along on my capstone journey, which really turned into a personal mission. We're going to look at how to design simple, low-cost engineering solutions for severe urban pollution. We'll look at the data, the actual on-the-ground interventions, and discover how smart civil engineering isn't just about, pouring concrete. It's really about protecting the air we breathe and the communities we live in.
So, Section 1. The hidden smog problem, and identifying the real culprit.
Now, if you've ever experienced winter in Lahore, you know the smog can be absolutely suffocating. We usually just blame the traffic, right? But visiting an air quality monitoring station at UET Lahore during my internship revealed a totally different story. Think about how construction sites operate. Every single time they excavate, cut, drill, or just leave loose soil sitting there uncovered, they're generating massive amounts of fine dust particles. We're talking PM10 and PM2.5. This isn't just a little dirt, it's a severe health hazard. What's happening is a process called aeolian erosion. The wind sweeps right across these exposed sites, picks up those microscopic particles, and carries them directly into our atmosphere over huge areas. It's actually a primary, direct contributor to that thick winter smog that cuts down visibility and damages our lungs. So the pollution is starting long before a building is even finished.
But you see, the wind is really only half the story. I want you to ask yourself a simple but pretty provocative question. Where exactly does all that exposed soil go when it rains?
Well, the answer introduces our secondary threat, which is hydraulic erosion. When heavy rain hits these unprotected construction sites, it washes all that loose soil and debris straight into the city's drainage systems. The contrast is just staggering when you look at a clean, freely flowing drain versus a drain completely choked with thick, heavy sediment. That untreated sediment acts almost like wet concrete inside our sewers. It causes massive blockages, which directly leads to water overflow and major urban flooding during the rainy season. We are quite literally washing our foundations away, contaminating our water, and causing devastating property damage in the process.
Which brings us to Section 2. What exactly is ESC? The engineering solution. Once we identified this dual threat of wind and water erosion during my capstone, the very next step was figuring out how to stop it at the source. Enter ESC. That stands for Erosion and Sediment Control. To put it simply, without all the heavy technical jargon, ESC is basically a set of incredibly practical, powerful practices used at construction sites to prevent soil erosion and trap sediment before it ever has the chance to become pollution. It's a total paradigm shift. Instead of trying to treat the smog or unclog the drains after the damage is already done, which by the way is incredibly expensive and inefficient, ESC focuses on preventative engineering. We keep the valuable topsoil on the site, exactly where it belongs, and that protects our air, our water, and our roads all at the exact same time.
Moving on to Section 3, Small Actions, Big Impact. Let's unpack the technical toolkit.
Take one of our most effective, yet beautifully basic tools, the silt fence. I mean, it looks so simple, right? It's literally just a temporary barrier made of geotextile fabric stretched between wooden stakes and installed right along the contour of the land. But its impact, absolutely huge. When runoff water hits this fence, the water is forced to slow down. The heavy sediment, that soil that would normally go choke our drains, just drops out and gets safely trapped right behind the fabric, while the clean water is allowed to just pass on through. It's this low-cost, elegant engineering solution that keeps soil on site and protects our city's waterways from turning into toxic mud pits.
Next up is dust suppression. The difference this makes is just undeniable. Imagine a dusty, completely unregulated site. It's an absolute nightmare for the respiratory health of anyone living nearby. Now contrast that with a site using basic dust suppression techniques. We're talking about simply spraying water on the roads and using organic covers for those big exposed soil stockpiles. It's a remarkably small action, but it yields us massive improvement in air quality. By just keeping the soil damp, we physically weigh down those tiny PM2.5 and PM10 particles, so the wind simply can't pick them up. It's an immediate, massive win for public health.
Now, let's trace this really fascinating chain reaction when it comes to stabilized construction entrances. You've probably noticed how the roads right outside a construction site are always completely caked in mud, right? Well, here is the life cycle of that mud. Heavy trucks drive through the messy site. The wet soil sticks to their massive tires, and they track it straight out onto public roads. The sun then bakes that mud completely dry, the street traffic pulverizes it, and then the wind whips it right back up into the air as choking dust. So, what's the solution? A stabilized entrance made of clean, angular gravel. As the trucks drive over this gravel, it literally scrubs the mud right off their tires before they ever hit the pavement. The sediment stays on site, the public roads stay clean, and that entire cycle of airborne dust is stopped dead in its tracks. No way around it, it's a real game changer.
All right, Section 4, the cost of doing nothing and why this is a smart investment.
You know, sometimes there's pushback against these controls because contractors see them as just another extra expense. But the crucial point is really captured in this comparison. Without ESC, society pays a massive hidden tax. We're paying for it in frequent, highly expensive municipal drain cleaning. We pay for it in flood damage to our homes and businesses. And we definitely pay for it with our health. Think of all the respiratory diseases caused by that smog. But with ESC, the script flips entirely. We get cleaner roads, significantly less dust, and a protected ecosystem. That relatively small investment a contractor makes in, say, some gravel and geotextile fabric, it literally saves municipalities immense amounts of money in cleanups and public health crises down the line. It's simple. Prevention today means much lower costs tomorrow.
So, let's see how this all builds into a standardized, replicable approach. During my capstone, I didn't just want to suggest a bunch of random tools. I really wanted to build a solid system for the department that could be baked into future construction tenders. So, we developed a 5-step ESC framework. Number 1, you assess the site's erosion and sediment risks early on. 2, plan out the specific control measures needed. 3, implement them properly, right there on the ground. 4, monitor them regularly through site inspections. And 5, maintain and improve them based on real-time site conditions. This takes environmental protection from being this vague, nice-to-have idea and turns it into a strict operational checklist.
And when we actually apply this framework, the quantifiable benefits are undeniably powerful. We're looking at a significant reduction in airborne dust and PM10 emissions, which drastically cuts down on that winter smog. We get controlled sediment runoff, which equals much cleaner drains and a far lower risk of flooding. And that directly leads to reduced siltation of our sewers, which means lower municipal maintenance costs. We're preserving soil health, protecting our waterways from pollutants, and ultimately building stronger policies that benefit communities across the entire province. This project absolutely proves that these low-cost engineering interventions yield massive environmental and financial returns.
Finally, Section 5, a greener Punjab tomorrow and sustainable development.
Small engineering solutions can solve big environmental problems. This really became the defining lesson of my whole internship. Before this capstone project, it was so easy to think civil engineering was strictly about, calculating loads and designing strong structures. But it is so much more than that. It's about designing sustainable systems that interact harmoniously with nature, systems that actually protect people. Good engineering builds things, sure, but smart engineering protects things. We are designing the lungs and the arteries of our cities, and it is entirely our responsibility to keep them clean.
Let's zoom out to the big picture here. Implementing these smart infrastructure and dust suppression initiatives isn't just happening in a vacuum. It's a highly critical piece of Punjab's larger vision for climate resilience. It feeds right alongside things like tree plantation drives, promoting renewable energy, and better solid waste management. Smart construction today essentially guarantees a breathable tomorrow for all of us. But it does leave us with a really critical question to end on. If the solutions to our urban smog and flooding are truly this simple, this low cost, and this incredibly effective, isn't it time we made them a mandatory part of every single brick laid in our cities?